Our next topic is understanding how energy is transported inside of stars. We're going to start by talking about radiation and opacity. Well, let's talk about why we need to know this. We know it takes time for the energy to get out of the star. We know that because we've looked at how long it's going to take for stars to collapse. And it takes a certain amount of time for that energy to get out of the star. But what is the thing that is causing it to be so slow? Well, the energy is mostly coming from inside the star, and that energy has to get to the surface to be able to escape. And so to get there, that means you've got to have a photon travelling from somewhere inside the star up to the surface. And if it could just go, say, from the centre of the sun to its surface, it would only take 2 seconds. But it can't do that directly. So we're going to look at the reasons behind it taking so much longer and how long it should take. So how long does it take for the energy to escape? Well, the photons are going to be absorbed by atoms or bounce off of atoms or electrons a very short distance after they're emitted. And so what you get is that photons don't take a straight path to the surface. And what we have is we have a mean free path. That is, it'll go a different distance each time. It's, you have a new photon that's emitted, and then it's absorbed by the next atom, and then it's emitted again. But it's going to have an average distance it can go, and that's the mean free path. And once you have an absorption, so you've got your photon that's absorbed, that atom stays excited for of the order of 10 to the minus 8 seconds, so 100 millionth of a second. And then it will re-emit. So there's the time, a finite time it takes for each of those particular reactions, each of those particular interactions. So we have this random walk because the photon could be emitted in any direction, so it doesn't necessarily keep going in the same direction after it's been absorbed and re-emitted, and it's going to take time to do each step. So let's work out how long it takes to do each step. Well, let's think about the sun. We've got the density of the sun as an average. We're just going to assume it's average all the way out through. We'll get into the details of how it's different in different parts of a star later. But we know what the density of the sun is. It's a little more than water, 1.4 grams per centimetre cubed, which if we translate that into particles is about 10 to the 24 particles per centimetre cubed. We also know what their absorption cross-section is. What that means is that if you have a particle, it's got an effective area for how close a photon has to get to it in order to be absorbed. And so this cross-sectional area is 10 to the minus 24, 2 times 10 to the minus 24 centimetres squared. And what that means is that, let's say you've got a column, you're looking down this thin column of gas into the sun, and it's 1 centimetre squared. And that means that to cover the entire area with particles that can absorb, you need 5 times 10 to the 23 particles. It's just the inverse of the cross-section. What that means is if you compare that to the actual density of particles, you've got 10 to the 24 particles per centimetre cubed, that means that a photon is only going to travel of the order of half a centimetre before it hits a particle. So this is basically saying that on average, a photon will go half a centimetre, then it'll get absorbed. When it's re-emitted, you don't know what direction it's going in, but it'll still take that mean path of half a centimetre. So that's our mean free path. Okay, so how does that help us? Well, we've got to figure out how many times that's going to happen on its way to the surface. And so you've got to think of it like this. You've got a situation where you've got an atom, it's emitted a photon, and then it's going to be absorbed here. And then it's going to be re-emitted in some other random direction, and it's going to be absorbed. And then it'll be emitted and absorbed, and emitted and absorbed. And what you want to work out is how much does it travel in this one direction. So what's the average distance travelled in this one x direction based on this random walk. And this is a statistical thing. And basically what you get is that this change in x is given by the square root of z times the mean free path, where z is the number of absorption and emission, re-emission processes. So you think of it as it's moved a mean free path, it's moved a mean free path, it's moved a mean free path, it's moved a mean free path. It's done it 4 times. And so this distance should basically be twice the mean free path. So that means that we should be able to work out, since we know how much distance we want it to move, we should work this out, right? We know that we want it to get, say, from the centre to the surface, so it has to move the radius of the star, in this case the radius of the sun, And we can work out, I'll go through this problem, so we can rearrange this equation to get that the distance, the number of absorptions, z, is given by the distance you need it to move divided by the mean free path squared. And this is just replacing this distance, which is our distance that's going to move in one direction, with the radius, that's the biggest distance it's going to move. And if we put in real numbers, this is the radius of the Sun, this is our mean free path based on the Sun, and we come out with this 10 to the 22 times. So you're basically going to do this process 10 to the 22 times before a photon gets to the surface. Okay, so we've got our number of times it takes, and we know that each emission takes about 10 to the minus 8 seconds. So it gets absorbed, and then it takes 10 to the minus 8 seconds before it re-emits. And so that means that you know how long it's going to take. It's going to take 10 to the 22 times 10 to the minus 8, which is 2 times 10 to the 14 seconds. And so what you get is that the photon will take that many seconds, which is about 6 million years. And so if it takes that long, it takes 6 million years for a photon to get from the center to the surface, you certainly can't expect a star to lose energy faster than that, so it can't collapse faster than that. And so remember, I'm talking about going from the center to the surface, so this is really more of an estimate of the overall collapse time. But basically this is helping you understand how we get this energy transport and why there's a finite time for a star to collapse under gravity when pressure builds up. But how is the energy actually transported? Is it really done like that through radiation, or is it done by some other means? We have 3 different forms of energy transport: conduction, convection, and radiation. Convection we'll get to in our next section. But for now, let's think about conduction versus radiation. Now, I'm going to put you all out of your misery and tell you that conduction is negligible. But let's talk about why, okay? At the densities within stars, you might think that conduction would be viable, but it's really not. You can think of conduction and radiation as being quite similar. You're talking about using direct interaction to get the energy transferred. So in the case of conduction, you're basically moving it by moving particles. So the particles are touching each other and that passes on the energy. In the radiation version, the particles emit photons, so it's done by means of the photon carrying the energy. So which of those mechanisms should be dominant within stars? Well, you already know the answer, but let's look at it in a little more detail. So the energy of a particle, the average energy of a particle, is given by 3/2 kT, where K is the Boltzmann constant and T is the temperature. Likewise, your photons have an energy of Planck's constant h times the speed of light over the wavelength. And it turns out that basically if you look at the distribution of wavelengths and temperatures, you have a similar sort of energy. So that really doesn't help you very much. The number density of particles is much greater than the number density of photons. So that might suggest that actually you could do things via conduction. You've got much higher energy density in the particles, but the big deal is the mean free path. So what you've got is that when you have photons, they can travel of the order of a centimeter, right? We had 0.5 centimeter for the Sun, but of the order of a centimeter for a photon, whereas at these high densities, you're only going to have your particles moving of the order of an atom size before they hit each other. And so your mean free path is very small for the particles and very large for the photons. So it means that the photons basically can do a much better job of moving significant amounts of energy from a high energy to a low energy environment. And so conduction really doesn't help you. Obviously it's going to happen a little bit, but it's such a negligible effect that you can basically say it's done by radiation. So we've got that radiation is the way in which we're moving our energy. But we also have convection. And to decide which one of those is going to dominate, we need to think about, well, what is going to prevent you from having radiation moving? And it's basically the opacity. How opaque is your material? If the material is opaque, it stops the radiation from flowing. So opacity is just a measure of the resistance of the flow of radiation, and it's very temperature dependent. When we have high opacity, it means that radiation doesn't flow, so you get an energy buildup. And so what happens is that the gas will move itself, and the energy will be moved by moving the gas particles rather than by moving photons. If it's low opacity, then it's easy for the photons to move, and so you don't get the same heating up, and you move things by radiation. So when you have high opacity, you have convection. When you have low opacity, you have radiation. So let's talk a little bit about opacity. Like I said, this is really a measure of how able is something to absorb radiation. So you can think of something like, say, glass windows do not absorb very much visible light, whereas bricks are pretty good at it because they don't let the light through. Likewise, graphite as carbon is black. It obviously absorbs nearly everything that falls on it in visible light, whereas diamonds are transparent. So, you know, it can be quite subtle whether something is opaque or transparent. In any case, with most things, we can only see a certain distance. Even with like a big glass thing, once you've got enough glass, you won't be able to see through it anymore. It's just too thick. And so you can also think of this in terms of fog. If you think about fog, you've got stuff that's stopping you from seeing all of the photons. So the photons get scattered out of the way. And at some distance into the fog, you stop being able to see any further. And that's a way of measuring what the opacity of the stuff is. So at some distance into whatever your medium is, you have a constant scattering of light. And it's either being deflected or absorbed and re-emitted. In fact, when we look at the surface of stars, that's what's going on, where you have hydrogen atoms that are gaining and losing electrons. So you can go from having an ion, where you have just proton, to having a neutral hydrogen, to having a hydrogen with an extra electron. You think about it, has more stability when there are 2 electrons in that shell, so it can gain it, but it's easy to knock it off again. And it's because you're going from not having an electron attached to having an electron attached to having an extra electron, the energies involved means that you get continuous radiation being absorbed and emitted. Okay, and so that makes it opaque, or nearly all wavelengths. Now opacity, which I'll warn you now, there are lots of different ways of defining it. In my case, I'm going to use kappa. The subscript lambda is because it is wavelength dependent. So it's kappa subscript lambda for opacity, and it's measured in meters squared per kilogram. So it's basically what is its cross section in terms of its mass. How able is it to block light? As we've already said, it's very temperature dependent. If you have a high temperature, you tend to have low opacity. If you have a low temperature, you tend to have high opacity. But that's not always true either. So we'll come back to that. Okay, so let's talk about opacity. I've got some flux here that's got some wavelength dependence. So it's flux at some wavelength and it's hitting a slab of material. The slab of material has a thickness dx. It has a density rho, it has opacity kappa, and a temperature T. Some of the radiation hitting it doesn't make it out the other side. So what we have out the other side is F prime, and this is the flux that makes it out. The difference between what made it in and what made it out is how much gets absorbed or deflected inside of this slab. And so you have a difference in the flux that's given by this equation, where what matters is the opacity and the density and the amount of flux hitting it in the first place, and how thick this is. So dr here and dx here, because I'm thinking about stars. So here I've got, just rearrange this so that my fluxes are all on one side, and now I can integrate this, and I end up with that basically as this flux goes into here, it's going to start with F0 and it's going to get less and less and less as stuff gets absorbed. And so what we get is that what comes out the other side has been decreased exponentially according to how thick this thing is, that's R, what the density is, rho, and the intrinsic opacity of the particles. And so you're going to have a characteristic mean free path, which is given by kappa and rho. This is basically, again, how far does a photon get before it gets deflected or absorbed. And we're going to have different ways in which different types of photons are going to be interacting. And so it depends on what this is made of, and we're going to get a wavelength dependence for how it absorbs. But this helps us understand what's going to happen in terms of opacity and getting the energy to be stored in here or the energy to just go straight through. If the energy is stored in here, we're going to get convection. If the energy goes straight through, we're going to get radiation as our major source of energy. Now, because the density tends to go down, density decreases pretty fast with radius because that's also exponential. Remember that we've got pressure dependence and hydrostatic equilibrium, and so actually the opacity is generally going to be dominated by this intrinsic force, this intrinsic thing, kappa, which is also called opacity. Sometimes it's called the mass absorption coefficient, sometimes it's just the absorption coefficient. We like to use the same words to mean the same thing, and it's very complicated. Okay, so what is it that actually causes the opacity? What are the actual interactions going on? Well, photons can interact with particles in the gas, right? And it depends on what it is. So if you've got high temperatures, you might have lots of electrons because you've ionized a lot of your gas. And then you're going to have ions as well. If it's at low temperature, you might have lots of neutral atoms. And it depends on what atoms you've got as well, as to how many electrons are free, and so on. And so you can have all of these things going on. At high temperatures, you're going to tend to have lots and lots of electrons, because that's when you're able to knock lots off of the different atoms that you've got. And that's what tends to matter. At lower temperatures, then you're going to have the ions and the neutral atoms that will, and in some cases, molecules close to the surface. Then those are the things that are going to have those interactions and contribute to the opacity. So what are we actually talking about here? Well, there's a few different ways of looking at this. We can have electron scattering. Basically, this is where an electron is going to be hit by a photon, and the photon gives up some of its energy to the electron and is deflected. We actually call this Compton scattering, and this is showing it schematically. So I've got this X-ray photon, it's a high energy photon, it hits an electron and it gets deflected at some angle, and it will also have a different wavelength, and the electron has taken some of the energy. And so what we get then is a change because the electrons are there. So the X-ray photons are going to bounce off the electrons. There are other things that you can have. You can have free absorption. Well, it's called this because when you have the electron, it's free to start with and it's free at the end. It's never bound to a nucleus, but it goes close to one. So if you think about, you've got an electron, it's negative. You've got an atomic nucleus, it's positive. It's attracting this thing, but the free electron is moving fast enough that instead of being captured, it just changes direction, but still has the energy to escape. And so you have what you can think of as a hyperbolic orbit. It's never captured by the nucleus, so you don't get it bound to the nucleus, but because it accelerates, it changes direction, it has to emit a photon. And this is called Bremsstrahlung or inverse Bremsstrahlung, which actually comes from the German for breaking. And so it's not quantized because you can have any energy of electron to start with and any energy of electron to finish. So it's going to be something that gives you a continuum. Okay, it's not something that gives you nice lines. The interaction has to conserve both energy and momentum, and so that determines what direction it goes in and how much energy is released in a photon. Like I said, the Bremsstrahlung means breaking radiation, so you can think of it as it's changing direction, it's decelerating or accelerating, and so that's where it comes from. Okay, other interactions. Well, you can have a bound-free interaction. So you can think of it as you've got a bunch of atoms with electrons, and you can use the energy to ionize your atoms. The electrons are going to come off, and at the same time you can also have free electrons being recaptured, and they have to give off a certain amount of energy. But because the electrons after ionization can have any energy, and because the electrons, when they recombine, just emit the photon that gets them to the right energy to be bound, well, then you're going to get continuous radiation, right? You're going to get something that is above the level that it needs to be it has to give off all of its energy or gain enough energy to be thrown out. Whereas bound-bound absorptions, this is basically what we talked about before in terms of spectral classifications and the Balmer series and things like that. You've got an atom, it's got electrons, and as they jump up and down, then they have to absorb or emit photons. In this case, the electron is always bound. And this is very much quantized. It can only be certain energies. So if you've got an ionized gas, you're basically really good at getting all wavelengths of light. And so what you've got is that you've got all of these electrons, you've got these atoms, you can do photoionization and you can do recombination, and that means that you've got a constant flow of all energies of light. And so that means that you can't see through it. If it's a neutral gas, it can become very transparent because it can only absorb certain wavelengths, except for the stuff above its ionization. So if you have an ionization potential, below that, it can only absorb the photons that are for the transitions within the atom. But above ionization, it can absorb everything. Okay. So the last thing that we're going to look at in this section is we're going to look at an example of photoionization and what sort of temperatures we're talking about. So I'm thinking about temperatures above 100,000 Kelvin. What ionization potentials are we looking at? Well, let's just consider hydrogen and helium for now. For hydrogen, you need to give it 13.6 eV. If the electron is in its lowest state, that's how much energy it needs to be ionized. For helium, you have 2 electrons, so you have 2 things that you need to knock out. The first one takes 24 electron volts, and the second one is 54. So we can work out what temperature the gas needs to be at to ionize the gas. You can think of it as being, you've got these particles, and these particles can collide and provide the energy to ionize this material. And in that case, what you get is something that is completely ionized. So we're going to say that this energy has to equal 13.6 eV. And so we can rearrange it and put our 13.6 eV in here. This is the Boltzmann constant. And if we rearrange it, we get of the order of 10 to the 5 Kelvin. So at 10 to the 5 Kelvin, we should have enough energy to completely ionize the gas. If you do the same thing to completely ionize helium, remember I've got 2 electrons, so I need to get rid of this one and this one. I need a full nearly 80 eV, and this comes up to more like 600,000 Kelvin. However, you don't need to be that hot. So if you're up at around 30,000 Kelvin, you've already got a significant number of photons, of things that are moving that will let you get to 13.6. And this has to do with the fact that you have a Maxwellian distribution of velocities, so even though the mean, the root mean square of the most likely velocity is way lower than this 13.6, you can actually do a lot of ionization because you've got a lot of particles that are moving faster. And likewise here, you don't need to get up to quite these temperatures. So that kind of gives you an idea of what's going on in terms of generating opacity inside the stars. The next thing that we'll be doing is talking about where convection fits.